Some other characteristics also relate to that high water use efficiency, and these are the resin ducts. So they have these resin ducts on the leaf, and that leaves a layer of resin all around the outside of the leaf. This makes them highly flammable, of course. So their ecology actually relates to this. Yep.
Is this just for the hummock grass?
This is just the hummock grass. So that also prevents cuticular transpiration through the side of the leaf without the stomata. And it's also related to the indigenous and industrial uses of this plant, because the indigenous uses are for insulation, resin adhesives, and fiber crafts. So basically it's taking advantage of the physiology of this plant, which allows it to thrive under the most incredible conditions for grasses, and using those properties for uses, as well as potential industrial uses related to polymers and biocomposite products. The third Australian plant that I'm going to bring up is the river red gum, groundwater dependent. We've talked about it a little already. So, with the groundwater dependent trees, you can say, well, water is no longer limiting. Soil water availability, it doesn't matter. Then what can control evapotranspiration? And it's only three things: solar radiation, vapor pressure deficit, and wind speed. And I've marked vapor pressure deficit because both high temperature and low humidity can affect evapotranspiration or transpiration, but they're combined into this vapor pressure deficit term. Last lecture, stress and mortality. Almost there. This time I got the photos in the slide. Plant responses to stress. There are three primary responses of plants to environmental stress. The first type that we'll talk about are escapers. Escapers completely finish their life cycle before stress occurs. And so in these pulse-driven systems like Central Australia and southwestern North America, it'll be dry as for however long. Then you'll get a big rain, and you'll get all these ephemeral plants coming out. And they will go through their entire life cycle and set seed before the water that they receive from that pulse of rain diminishes. That is one strategy. Second strategy is avoidance. Two types of avoiders: red gums, groundwater dependent plants, but also drought deciduous plants. So what I'm showing you here is a drought deciduous plant from Arizona, common name ocotillo. This plant is alive, but during a dry period. It rains, and it grows all these leaves, sprouts out heaps of leaves. Then the environment dries again, it goes back to basically a dead stick, and then back to leafy, back to a dead stick. It can do, ocotillo can flush out a new flush of leaves up to 10 times a year, depending on the precipitation pulse patterns. And finally, tolerance. Tolerance is probably the most studied. It's the most important for agriculture, and tolerance is just being able to live with the stress and continue functioning. So here what we're showing you is rice. So this is a wild type rice with no water stress. This is a wild type rice with water stress, not doing too well really. And this is a transgenic rice with water stress. And so what they're doing is, transgenic. So what they're doing is they're looking at the genes of crops to try and improve tolerance. Improving tolerance, stress tolerance in crops is a big, big issue, because something like 20% of our potential yield we don't even get because of crop stress. And this helps, also to help mitigate stress from climate change due to increasing heat and drought. Natural tolerance, we can see adaptation in natural tolerance too, and in the formation of biomes. So what I mentioned before is, for example, tropical forests tend to experience a lot of shade stress. They also tend to be, those plants are tolerant to shade stress, but they're not very tolerant to high light stress. And so where plants grow, they've actually adapted to be tolerant to the types of stress they experience in that location. Now I'm going to focus on drought, and specifically on what happens during drought. So the first thing that happens during drought is that water potential goes down. So water potential becomes more negative. Second, leaf expansion ceases. Leaf expansion ceases almost immediately. This is because you need turgor to push this, the cells apart to make them bigger. Without that turgor, you have no growth, and so growth is the first thing to go. Then, some while later, photosynthesis starts to decline, and then once photosynthesis is really getting close to being done itself, that's when you see phloem transport stop. Phloem transport continues after almost everything else shuts down. And once phloem transport stops, that's pretty much all she wrote. Then we also talked about isohydry, anisohydry, and mortality. Isohydric plants do not maintain a constant midday water potential by closing their stomata during drought. And so that's what you see here. This is an isohydric plant. Their midday water potential does not change regardless of what the soil water potential is. As opposed to anisohydric plants, which have fairly high fairly high water potential when the soil is wet, but then when the soil dries, their water potential plummets. They do not close their stomata completely when they experience water stress, and that allows the water stress to continue to get worse and worse and worse. This is also related to midday depression of stomatal conductance. So midday depression is really common when you in plants which experience stress, particularly isohydric plants, because remember the isohydric plants will close their stomata at midday as they start to experience high vapor pressure deficit and low soil water content. So some plants are more like anisohydric plants when they're wet, when they're well watered. Others are already starting to show this isohydric behavior. So there's a big range, a huge continuum of plants from one extreme to the other in the way that they can deal with water stress and either protecting or risking their stomatal conductance, or sorry, their hydraulic architecture, their hydraulic conductance. And this also brings us to stomatal optimization. So remember, I've been talking about water use efficiency and how as stress increases, water use efficiency goes up, because as stomata close, the transpiration declines faster than the photosynthesis. Well, what we can stomatal optimization derives from the premise that plants optimize the amount of water they can take up for a given cost of transpiration. So given their hydrologic niche, so given their water availability, they will maximize carbon uptake while avoiding using too much water. So water use efficiency scales with the inverse of the square root of vapor pressure deficit. Don't worry about the square root, don't worry about any of that. Basically what that means is that as D increases, stomatal conductance and water use efficiency go down, because it's the inverse. And also remembering that transpiration declines more than photosynthesis when stomata close. And this is why you get these relationships versus 1 over D. This one is also versus 1 over D. It's just moved the axes. And these are showing 2 Australian plants, red gum, and both of these are for mulgas. So, we're talking about heat, we're talking about high vapor pressure deficit, we're talking about low humidity, and we're talking about all of that because they are all interrelated. So basically vapor pressure deficit is affected by how much water the air can store, and hot air can store more water, by how much water the air is actually storing, which is related to the level of humidity and to the temperature. And so the vapor pressure deficit, you can imagine as temperatures go up, these vapor pressure deficits will also go up into the future. So we expect to have more severe droughts going forward. And this is kind of what we're showing here. So in the current climate, as the current climate moves toward higher temperature and less precipitation, we expect to see more mortality. And that is, in fact, what we have been seeing for the last 10 years. And that is it. That is the subject in about 70 minutes. Yes? Yeah, I'll post those today. There's not a lot different from the lectures other than the order that they're in. And I deleted all the others. I think so.
Would it be useful for you to have a link to share to the sound recording of today's lecture? Just the sound.
Would you guys like that? The audio for the lecture?
Yes.
And you asked a question during the lecture, so we need to find out if you're okay with your voice being on the recording.
That's cool.
Okay.
Yeah.
Are the exam papers online on the UTS library, are they similar to what the exam paper will have?
They are not in the library, and yes.
Online?
Will you post some?
Post some exam questions.
Or like some type of exam paper?
Yeah.
Practice paper.
I could
In the library?
post some of the questions that I deleted from this year's exam. That would probably be fair. But then again, they're topics that, they're generally topics that Derek covered and I wasn't planning on covering.
Yeah, it'll just confuse us.
Yeah, I'd rather not confuse you. There's enough information.
There is. I'm just going to turn this off.
So, and if you have any questions on, it looks like I do have all of them here, if you have any more detailed questions.
Yeah.